Here is a challenge for you. Name a substance that simultaneously performs all of the following. It determines the age of our planet with an accuracy of within 1%. It has been heating the Earth from the inside out for the last 4.5 billion years. 2 billion years ago, without a single engineer or a single blueprint, it assembled itself into a functioning nuclear reactor in the middle of the African jungle. It provided electricity to billions of people and is currently flying through interstellar space on board a spacecraft launched nearly half a century ago. This is not a collection of different materials. This is the biography of a single element. Its name is uranium, element 92 of the periodic table. Before we continue exploring the reality of this metal and how it fundamentally changed our understanding of the universe, please take a moment to subscribe to the channel and hit the like button. It is a simple action that helps us continue producing these deep dive analyses of the hidden forces shaping our world. Before we move into what humanity has done with this metal, we have to talk about where it actually came from. The history of its origin is not just a beautiful picture of the stars. It is an event of such magnitude and violence that scientists spent decades arguing whether it was even possible, and only in 2017 did they receive a final, definitive answer. On August 14, 2017, two detectors of the LIGO Observatory, one in Louisiana and the other in Washington, simultaneously recorded the faintest ripples in space-time, a gravitational wave. Just 1.7 seconds after it, a flash of hard gamma radiation was detected. Optical, X-ray, and radio telescopes around the world immediately pivoted toward that point in the sky. The source was the galaxy NGC 4993 in the constellation Hydra, 130 million light-years away from us. There, two neutron stars collided and merged. A neutron star is what remains of a massive star after a supernova explosion. It is an object the size of a small city, but with a mass exceeding that of our Sun. The matter is so compressed that 1 cubic centimeter weighs hundreds of millions of tons. When two such objects collide, it is called a kilonova. The spectral analysis of the GW170817 flash showed that the cloud of scattered matter contained gold, platinum, and uranium. A lot of uranium. It is precisely in such collisions that the heaviest elements of the universe are born. During a kilonova, the density of matter is so monstrous that atomic nuclei capture free neutrons faster than they can decay. In a fraction of a second, the nuclei gain mass and turn into heavy isotopes. Uranium is one of them. Before the discovery of GW170817, physicists assumed this mechanism theoretically. Afterward, they saw it in action. Somewhere in our galaxy, or a neighboring one, billions of years ago, such a collision occurred. A cloud of matter with uranium inside scattered through space, drifted, and mixed with other clouds of gas and dust. About 4.6 billion years ago, one of these clouds began to collapse under the force of gravity. From it came the Sun and the planets, including the Earth. Before talking about what this decay does to the planet, it is necessary to tell how people found it at all. The history of the discovery of uranium is a chain of accidents, each of which might not have happened. Berlin, 1789. German chemist Martin Klaproth is working with a mineral that the miners of the Saxon mines called pechblende, pitchblende. It was mined in the silver mines of the town of Yakimov, in what is now the Czech Republic. There was no silver in it, hence the name, blend, or a deception. It was mined and thrown into the waste pile. Klaproth isolated a yellow powder from it, conducted an analysis, and decided that he had found a new metal. He named it in honor of the planet Uranus, discovered by William Herschel in 1781. It was the first planet discovered with a telescope, an event that was echoing through the scientific world at the time. But what Klaproth isolated was not a pure metal, but its oxide. The real metallic uranium, silvery grey, heavy and shiny, was first obtained by the French chemist Péligot in 1841. He reduced the metal from uranium tetrachloride using potassium. The density of the resulting substance is 19.1 grams per cubic centimeter. For comparison, lead is 11.3 and iron is 7.8. Uranium is almost twice as heavy as lead. What did humanity do with this discovery? At first, we started making beautiful dishes out of it. Uranium glass, with additions of uranium oxide, gave a beautiful yellow-green color and a characteristic glow under ultraviolet light. It became a fashionable commodity in the 19th century. Vases, glasses, and decorative saucers were produced in Bohemia and sold throughout Europe without any precautions, because no one in the world yet knew that this material constantly emits something. The concept of radioactivity did not exist. Paris, March 1, 1896. Physicist Henri Becquerel develops a photographic plate that had lain in a desk drawer for several days, next to crystals of potassium uranyl sulfate wrapped in black paper. The plate is exposed. A clear imprint of the crystals is visible. Becquerel was studying phosphorescence. He planned to check if uranium salts emit X-rays after exposure to sunlight. Wilhelm Röntgen had discovered his rays in 1895, and it was the main scientific sensation of the time. For several days, there were clouds over Paris. Becquerel put the construction in a desk drawer and waited. Then he simply developed the plate without waiting for the sun. There was no sun. There was no phosphorescence, but the plate was exposed, sharply, clearly, as if the crystals had been lying under direct light for hours. Uranium emitted radiation on its own, without any external source of energy. Becquerel discovered radioactivity by accident because of the cloudy Parisian weather. He conducted a series of control experiments, became convinced of the result, published an article, and basically stopped there. The nature of the phenomenon remained a mystery to him. The scientific community treated it without much enthusiasm. For 2 years, it was almost forgotten, until a young woman decided to choose this topic for her doctoral dissertation. Marie Skłodowska came to Paris in 1891 from Warsaw. She had almost no money. She spent her first winter in an attic where, in severe frosts, the water in the basin froze by morning. She attended the Sorbonne, the physics faculty. She was the first female student in this faculty in the entire history of the university. Then came marriage to the physicist Marie Curie and joint work that overturned physics. Pierre constructed a precise electrometer. Marie took it and began to systematically measure the intensity of radiation from various uranium compounds. She gathered precise quantitative data, comparing samples, and discovered something that was unsettling. Pitchblende, the very mineral Klaproth worked with, emitted radiation significantly more strongly than pure uranium salts with the same amount of uranium. If radiation is a property of uranium, then the intensity should be strictly proportional to its quantity. But pitchblende gave significantly more. Most scientists in her place would have decided that they had made a mistake in the measurements. Marie drew a different conclusion. In this mineral, there is another element, unknown, which radiates more strongly than uranium. In 1898, the Curies discovered polonium, named after Marie's homeland, Poland, which at that time was not on any map. Then they discovered radium. The very word quote 3 was coined by Marie from the Latin radius, meaning quote 4. In 1903, Marie Curie, Pierre Curie, and Henri Becquerel received the Nobel Prize in Physics. In 1906, Pierre died, hit by a horse-drawn carriage on a Paris street. In 1911, Marie received a second Nobel Prize, in chemistry. She was the first person in history with 2 Nobel Prizes in different scientific disciplines. Marie Curie died on July 4, 1934. The diagnosis: aplastic anemia. decades of work with radioactive substances without any protection. Back then, they simply didn't know it was needed. Her personal laboratory notebooks are kept in the National Library of Paris in special lead containers to this day. A researcher who wants to study them is obliged to sign an agreement on risks and work in a protective suit. The records of a person who died 90 years ago are still dangerous to touch. After Curie, physicists took up the next question: what exactly is happening inside the nucleus? In 1911, Ernest Rutherford in Manchester bombarded thin gold foil with alpha particles. Most flew right through, but some bounced back. Rutherford compared this to firing an artillery shell at tissue paper and having the shell suddenly fly back at you. His conclusion: an atom is mostly empty space, but in the center is a tiny, incredibly dense nucleus. This was the discovery of the atomic nucleus. In 1919, Rutherford first artificially split an atomic nucleus. He bombarded nitrogen nuclei with alpha particles and obtained oxygen nuclei and protons. It was the first man-made nuclear decay. He realized that inside the nucleus, energy is concentrated that is incomparably greater than in any chemical reaction. But he also publicly claimed that it was practically impossible to use this energy, that anyone who saw a source of energy in the atomic nucleus was talking nonsense. One of the greatest physicists in history was wrong. And he was wrong precisely because in 1919 there was not yet the discovery that would change everything. That discovery would involve the neutron, and it would lead us from a quiet laboratory in Paris to the most destructive weapon ever conceived. In 1932, the world of physics was quietly shattered by James Chadwick, working in Rutherford's laboratory. He discovered the neutron, a particle with no electric charge. To understand why this was the most dangerous discovery in history, you have to look at the geometry of the atom. The nucleus is guarded by a massive electrical shield, the Coulomb barrier. It is a wall that repels anything positive. If you try to fire a proton into a heavy nucleus like uranium, the nucleus simply pushes it away. But the neutron carries no charge. For the neutron, the electrical walls of the atom do not exist. It passes through the outer defenses of the element like a ghost walking through a brick wall. It was the perfect key, but in 1932, no one yet knew which lock it was meant to open. In 1934, Enrico Fermi, working in Rome, began a methodical campaign to bombard every element in the periodic table with these new neutrons. He worked through the list like a clerk, moving from light elements to heavy ones. When he finally reached uranium, he obtained radioactive products that he couldn't identify. Fermi assumed he had synthesized __5__ elements, metals heavier than uranium that didn't exist in nature. He was so convincing that he was awarded the Nobel Prize in 1938 for this work. The irony is profound. Fermi received the highest honor in science for a mistake. He hadn't made uranium heavier. He had done something far more radical, but he lacked the chemical proof to see it. The real breakthrough happened in Berlin in December 1938, against a backdrop of rising Nazi shadows. Otto Hahn and Fritz Strassmann, two elite chemists, were repeating Fermi's experiments with extreme precision. What they found made no sense. Among the products of the bombarded uranium, they found barium. Barium is element 56, roughly half the weight of uranium. Hahn was a chemist. He knew his reagents. There was no doubt, it was barium. But physically, it was considered impossible for a nucleus to simply break apart. Hahn was terrified of his own results. He wrote a letter to his longtime collaborator, Lisa Meitner, who had been forced to flee Germany months earlier because of her Jewish heritage. Meitner was in Sweden, living in a small town called Kungälv. It was Christmas. Her nephew, the young physicist Otto Frisch, had come to visit her. They went for a walk in a snow-covered forest, Meitner on skis, Frisch walking beside her. In that quiet, freezing Swedish woods, they solved the puzzle that Fermi had missed. The uranium nucleus wasn't absorbing the neutron to become heavier. It was splitting. The nucleus of a heavy atom is like a drop of liquid held together by surface tension. When a neutron enters, it causes the drop to vibrate so violently that it pinches in the middle and snaps into two smaller drops. But there was a terrifying detail. When Meitner calculated the masses, the two fragments, the barium and the krypton, weighed slightly less than the original uranium atom. That tiny missing fraction of mass had been converted directly into energy. Using Einstein's famous equation, E equals mc squared, she calculated that a single uranium atom released about 200 million electron volts. On an atomic scale, this was an explosion of staggering proportions. It was millions of times more energetic than any chemical fire. Meitner and Frisch called the process fission, borrowing the term from biology, where it describes a cell dividing. The news hit the scientific community like a shockwave. When Niels Bohr brought the news to a conference in Washington in January 1939, physicists didn't even wait for the end of the lecture. They rushed to the nearest telephones to call their laboratories. They realized something that Meitner hadn't yet emphasized. If a uranium nucleus splits, it might release more neutrons. If those neutrons hit other uranium atoms, they would split too, releasing even more neutrons. A chain reaction. A self-sustaining fire that could consume an entire city in a microsecond. Leo Szilard, a Hungarian physicist living in New York, had been haunted by the idea of a chain reaction since 1933. He was a man who lived in a state of permanent foresight. While others saw a new source of energy, Szilard saw a weapon. He knew that the German scientists in Berlin, Hahn, Heisenberg, and others, were the best in the world. He knew they had the uranium. In a desperate attempt to warn the American government, Szilard and fellow physicist Edward Teller tracked down Albert Einstein at his summer home on Long Island. Einstein, the world's most famous pacifist, was convinced of the danger. He signed a letter to President Franklin D. Roosevelt, warning him that extremely powerful bombs of a new type could now be constructed. Roosevelt received the letter in October 1939, just as Europe was plunging into World War II. He authorized a small uranium committee and gave them $6,000. It was a pittance, but as the intelligence reports grew darker, the project transformed into a massive, secret industrial empire known as the Manhattan Project. It eventually cost $2 billion and employed 130,000 people, but its heart was a logistical nightmare, the isotope problem. Natural uranium is a mixture. 99.3% is uranium-238, which is stable and stubborn. Only 0.7% is uranium-235, the unstable isotope that actually undergoes fission. To build a bomb, you need the 0.7%. But the isotopes are chemically identical. You cannot use acid or heat to separate them. The only difference is that U-235 is slightly, 3 neutrons, lighter. To exploit this tiny difference, the Americans built a massive city in the woods of Tennessee, Oak Ridge. They used a process called gaseous diffusion, turning uranium into a highly corrosive gas and pumping it through miles of porous barriers. The lighter U-235 molecules moved through the holes a fraction of a percent faster. To get enough pure material, they needed thousands of stages. They built the K-25 plant, which at the time was the largest building under a single roof in the world. While Oak Ridge was filtering gas, Enrico Fermi was in Chicago, attempting something no human had ever done. He was building the first nuclear reactor. He chose a squash court under the bleachers of the University Stadium, Stagg Field. There were no cooling systems, no radiation shields, no bunkers. They simply stacked blocks of graphite meant to slow down the neutrons and inserted lumps of uranium. It was called Chicago Pile 1. On December 2, 1942, Fermi's team watched the dials. The chain reaction became self-sustaining. The Italian navigator had indeed reached the new world. But there was a second path to the bomb. While the reactor worked, physicists discovered that when uranium-238 absorbs a neutron, it doesn't always split. Sometimes it transforms into a new element, plutonium. Plutonium was even more unstable and even easier to use in a bomb. In Hanford, Washington, they built giant reactors specifically to cook uranium into plutonium, poisoning the land for centuries in the process. The scientific director of the project was Robert Oppenheimer, a man of literature and theoretical physics. He gathered the greatest minds of the century, Fermi, Bohr, Szilard, Bethe, Feynman, at a secret laboratory on a mesa in Los Alamos, New Mexico. They were working against a ghost. They believed they were in a race with Nazi Germany. It wasn't until late 1944 that they realized the German project had stalled, hampered by bureaucratic infighting and a lack of resources. But the Manhattan Project was an engine that could not be stopped. It had its own momentum, its own hunger. On July 16, 1945, at a site called Trinity in the New Mexico desert, the first plutonium device was detonated. The flash was brighter than 1,000 suns. The sand melted into a green glass called trinitite. Oppenheimer, watching from a bunker, famously thought of a line from the Bhagavad Gita. "Now I am become death, the destroyer of worlds." Less than a month later, the uranium bomb, Little Boy, was dropped on Hiroshima. It contained 64 kilograms of highly enriched uranium. In the second it took for the bomb to explode, only about 700 grams of that metal actually underwent fission. Less than a kilogram of matter was converted into energy, but that was enough to erase a city. 3 days later, the plutonium bomb, Fat Man, was dropped on Nagasaki. The war ended, but the uranium was just beginning its long, quiet watch. The same physics that destroyed those cities would soon be harnessed to power them. But as humanity moved into the atomic age, it would find that uranium is a metal that demands absolute perfection. It is a substance that does not forgive mistakes, whether they happen in a reactor in Pennsylvania or a power plant in Ukraine. We had tapped into the energy of the kilonova, and we were about to find out just how heavy that burden would be. The smoke over Japan had barely cleared before the world began to ask a desperate question. Could this force, which had just demonstrated the power to erase a city in a heartbeat, be used to sustain one instead? The transition from the destroyer of worlds to the provider of light was not just a scientific shift, it was a psychological one. Humanity was trying to domesticate a predator born in a kilonova. We were attempting to take the fire of the stars and trap it inside a steel kettle. The first victory in this new struggle didn't happen in a grand city, but in the desolate plains of Idaho. On December 20th, 1951, at a small experimental station called EBR-1, scientists watched as a circuit was closed. 4 ordinary light bulbs flickered to life. It was a humble, almost domestic scene, but those 4 bulbs were being powered by the heat of splitting uranium atoms. The men in that room applauded, but their joy was tempered by a profound realization. They had just proven that the most destructive material on Earth could be made to do chores. By 1954, the Soviet Union had connected the first true nuclear power plant to a civilian grid in the city of Obninsk. It produced only 5 megawatts, enough for a few thousand homes, but it was the start of an era of staggering optimism. The math was intoxicating. One 10-gram tablet of uranium dioxide contains the energy equivalent of 800 kilograms of coal, 400 liters of oil, or 350 cubic meters of natural gas. A single truckload of fuel could power a city for a year. No smoke, no soot, no dependency on the erratic rhythms of the weather. For a moment, In the 1960s and 70s, nuclear energy seemed like a clean, infinite horizon. But uranium is not like coal or oil. It is a substance that demands absolute, unwavering perfection. It is an element that exists in a state of permanent tension, and if that tension is released in a way we did not plan, the consequences are measured in centuries. The quote, _14, was about to collide with human fallibility, and the results would rewrite the geography of the planet. The first crack in the dream appeared on March 28, 1979, at 3 Mile Island in Pennsylvania. It wasn't a catastrophic explosion. It was a failure of a small valve and a series of human errors. The cooling water stopped flowing, and the uranium core began to melt from its own internal heat. A small amount of radioactive gas escaped into the atmosphere. Physically, the damage to the public was negligible. Decades of health studies have found no significant rise in cancer in the area, but the psychological damage was absolute. The trust was gone. In the United States, the construction of new reactors ground to a halt for over 30 years. Uranium had shown that even a minor mistake could trigger a national panic. 7 years later, the world learned what a major mistake looked like. On April 26, 1986, at 1:23 a.m., the fourth block of the Chernobyl nuclear power plant in northern Ukraine surged out of control. The reactor, a Soviet design known as the RBMK-1000, had a fatal technical flaw, a positive void coefficient. In simple terms, when the reactor got too hot and the water turned to steam, instead of slowing down, the reaction accelerated. It was a machine that, when failing, stepped on its own gas pedal. The explosion wasn't nuclear in the sense of a bomb. It was a steam explosion that blew the 2,000-ton lid off the reactor and ignited the graphite moderator. For days, a red glow hung over the ruins, not the glow of fire, but the glow of ionizing radiation so intense it ionized the very air. The graphite burned, lifting microscopic particles of uranium fuel and fission products like cesium-137 and strontium-90 into the atmosphere. The wind carried this invisible poison across Europe, setting off alarms in Sweden and Finland before the Soviet government even admitted an accident had occurred. Chernobyl was the moment humanity realized that uranium could reclaim a piece of the Earth. Today, the 30-kilometer exclusion zone remains a ghost kingdom. Nature has returned, but the soil and the trees carry a radioactive signature that will last longer than any modern government. The disaster killed dozens of firefighters and plant workers in the first weeks, and thousands more in the years that followed due to thyroid cancers and other radiation-induced illnesses. It was a grim reminder that when we split the atom, we are dealing with a ghost that cannot be bargained with. And then came March 11, 2011. Japan, one of the most technologically advanced nations on Earth, watched as a magnitude 9.0 earthquake triggered a massive tsunami. The wall of water overtopped the seawalls at the Fukushima Daiichi plant. The disaster was a masterclass in irony. The earthquake didn't destroy the reactors. They shut down perfectly as designed. But the tsunami destroyed the backup diesel generators meant to pump cooling water. Without cooling, the uranium fuel rods, even in a shutdown state, generate enough decay heat to melt through steel and concrete. Fukushima proved that even if our engineering is perfect, nature is not. We can build against the Earth, but the sea will find the flaw. 3 reactors melted down. Entire prefectures were evacuated. And while the death toll from the radiation itself was zero, the social and economic cost reached hundreds of billions of dollars. These 3 events, 3 Mile Island, Chernobyl, and Fukushima, have created a paradox in the human mind. If you look at the cold, hard statistics published in journals like The Lancet or Nature Energy, nuclear power is actually the safest form of energy we have ever created. It produces fewer deaths per terawatt-hour of electricity than coal, oil, gas, or even wind and hydro. Coal kills millions of people every year through air pollution, a quiet, constant slaughter that we have become accustomed to. Nuclear accidents are rare, dramatic, and terrifying, and our brains are not evolved to process that kind of risk. We fear the invisible demon of radiation more than the visible choking of smog. While we struggle with the ethics of building new reactors, nature reveals that it was an engineer long before we were. In 1972, at a mine in Oklo, Gabon, French geologists discovered uranium ore with an incorrect isotope ratio. The U-235 was missing. They investigated and found something that sounded like science fiction. 2 billion years ago, a natural nuclear reactor had self-assembled in the African mud. Back then, the concentration of U-235 in natural uranium was about 3%, exactly what we use in modern power plants today. Groundwater seeped into the uranium-rich rocks, acting as a moderator to slow down neutrons and start a chain reaction. The water would boil away, the reaction would stop, the rocks would cool, the water would return, and the cycle would repeat. This natural reactor ran for hundreds of thousands of years before finally running out of fuel. It is the ultimate proof that the physics of uranium is not a human invention. It is a fundamental property of the universe. But the most striking thing about Oklo is what didn't happen. The radioactive waste produced by that natural reactor, the plutonium, the cesium, the strontium, didn't move. For 2 billion years, it stayed locked within a few meters of where it was created, held fast by the surrounding rock. This experiment by nature is the primary scientific argument for deep geological repositories. It suggests that if we bury our nuclear waste in the right kind of rock, like the Onkalo facility being built in the granite of Finland, it will stay there safely for the 100,000 years it takes to become harmless. We are currently living with a massive legacy of this metal. By 2020, humanity had accumulated about 400,000 tons of spent nuclear fuel. It sits in pools of water and steel canisters around the world, waiting for a final home. It is a debt we have incurred for 70 years of electricity. But there is a final, hidden chapter to the story of post-war uranium. A story of how we turned our swords into plowshares in the most literal way possible. In 1993, Russia and the United States signed the Megatons to Megawatts agreement. For 20 years, highly enriched uranium from 20,000 dismantled Russian nuclear warheads was downblended into low-enriched fuel and sold to American power plants. For 2 decades, 10% of all the electricity in the United States was produced by former nuclear weapons. Every time a child in America turned on a light bulb or a student opened a laptop, there was a high probability that the energy was coming from a metal that had once been aimed at their parents' heads. It is perhaps the only time in history that a weapon of mass destruction was used to provide the warmth of a home. Uranium has moved from the center of a kilonova to the heart of a bomb, then to the core of a reactor, and finally to the wiring of our lives. It has defined the borders of our empires and the limits of our safety. But as we look toward the future, we find that uranium's job is not just on Earth. It is the fuel that is currently carrying our messages into the void between the stars, and it is the key to whether we will ever leave this planet behind. We have spent decades building steel cages to contain the power of uranium, treating it as an alien force we brought into our world. But the truth is far more intimate. Uranium didn't arrive with the Manhattan Project. It has been here, under your feet, since the very first day the Earth coalesced from a cloud of cosmic debris. While we debate the safety of nuclear reactors, we often forget that we are currently living on top of one. Earth is not just a cold rock floating in a vacuum. It is a slow-burning, 4-billion-year-old nuclear furnace, and uranium is its primary fuel. For a long time, geologists believed that the Earth was hot inside simply because it hadn't finished cooling down from its violent birth. It was thought to be a reservoir of __quote _ 24 __. But the math never added up. If the Earth were only cooling by convection and radiation, it should have frozen solid billions of years ago. It should be as dead and silent as the Moon or Mars. The reason it remains alive, the reason the ground beneath us moves, the reason volcanoes erupt, and the reason we have a breathable atmosphere is radioactivity. According to studies published in Nature Geoscience, approximately 50% of the total heat flowing out of the Earth's interior is __, quote _ 25 __. It is heat produced by the constant, relentless decay of isotopes in the mantle and the crust. The three main suspects are uranium-238, thorium-232, and potassium-40. Uranium is the heavy hitter in this lineup. Every second, trillions of uranium atoms in the rocks beneath you are snapping apart, releasing tiny bursts of kinetic energy that accumulate into a staggering planetary heat source. This nuclear energy is what drives the great quote _ 26 _ of the mantle. It creates the convection currents that push tectonic plates across the surface of the globe. Without the heat from uranium's decay, there would be no plate tectonics. There would be no mountain ranges, no ocean basins, and no recycling of carbon between the atmosphere and the Earth's interior. Uranium is the engine of our geography. Even more critically, this internal nuclear battery is what maintains our magnetic field. The heat from radioactive decay keeps the outer core of the Earth in a liquid, swirling state. This motion of molten iron creates a quote _ 27 quote, a planetary-scale electromagnet that generates our magnetosphere. This invisible shield is the only thing standing between us and the solar wind, a stream of high-energy particles from the sun that would otherwise strip away our atmosphere and boil our oceans into space. This is what happened to Mars. Mars lost its internal heat, its dynamo died, its shield vanished, and its life-sustaining atmosphere was sandblasted away by the sun. We exist because uranium is still _ quote _ 28 _ in the basement of our planet. But as uranium keeps the planet alive, it also reaches out to us in ways that are far more direct and, at times, far more dangerous. Within the long decay chain of uranium-238, a sequence of 14 transformations that ends in stable lead, there is one specific step that creates a ghost. Its name is Radon-222. Unlike the heavy metals that precede and follow it, radon is a gas. It is invisible, odorless, and chemically inert. It doesn't bond with the soil or the rocks. Instead, it seeps out of the cracks in the Earth's crust, rising silently through the foundations of our buildings. In the open air, it disperses harmlessly. But in the enclosed spaces of our homes, in basements, crawl spaces, and poorly ventilated ground floors, it accumulates. Radon is the second leading cause of lung cancer in the world, surpassed only by smoking. It is responsible for tens of thousands of deaths every year, many of them in people who have never touched a cigarette. When you breathe in radon, you are breathing in the breath of uranium. As it decays inside your lungs, it releases alpha particles that can damage the DNA of your cells, triggering the mutations that lead to tumors. In many parts of the United States and Europe, measuring radon levels is now a standard part of buying a house. It is a reminder that even if you live 1,000 miles from the nearest nuclear plant, the element number 92 is still interacting with your biology. Uranium also finds its way into our lives through the water we drink. It dissolves naturally into groundwater wherever the surrounding rocks contain it, which is essentially everywhere. While we worry about industrial spills, geogenic contamination is far more widespread. In parts of Finland, India, and Canada, well water contains uranium at levels far exceeding the World Health Organization's limit of 30 micrograms per liter. At these concentrations, uranium isn't primarily a radiation threat. It is a heavy metal toxin. It targets the kidneys, much like lead or mercury. It is a silent intruder in the most basic necessity of life. And it doesn't stop at the water. For over a century, we have been industrializing our food supply using phosphate fertilizers. The phosphate ores mined from the earth are almost always tainted with natural uranium. As we spread millions of tons of these fertilizers across our fields, we are inadvertently enriching our topsoil with element 92. This uranium is absorbed by the roots of plants, especially root vegetables and leafy greens, making its way from the industrial mine to the dinner plate. It is a slow, quiet accumulation that science is only beginning to map. But as uranium permeates our domestic lives, it is also our most loyal emissary in the stars. There are places where the sun is too dim to provide power, and where chemical batteries are too heavy and short-lived. In the freezing void beyond Jupiter, we rely on radioisotope thermoelectric generators, or RTGs. These devices are essentially nuclear batteries. They don't use a chain reaction like a power plant. They simply harvest the heat of natural radioactive decay and convert it into electricity. The Voyager 1 spacecraft, launched in 1977, is currently over 23 billion kilometers away from Earth. It has left our solar system entirely and is now moving through the interstellar medium, the space between the stars. Voyager is powered by plutonium-238, a substance that is manufactured in nuclear reactors by bombarding uranium-235. Without uranium, we would be blind to the outer reaches of our universe. The data we received from the rings of Saturn, the methane lakes of Titan, and the mountains of Pluto were all carried to us on a current of electricity born from the decay of atoms forged in a kilonova. Voyager 1 has been running for 47 years. It is a testament to the staggering energy density of these heavy elements. Long after the human race has changed or disappeared, those golden records on the side of the Voyager probes will still be flying through the dark, their nuclear hearts still warm, carrying the memory of a species that learned to talk to atoms. Uranium is the element that connects the deepest part of our planet to the furthest reaches of space. It is the fuel of our tectonic plates and the silent gas in our basements. It is a toxin in our water and a messenger in the void. We have spent 2 centuries trying to categorize it, to label it as a resource or a threat, but uranium remains indifferent to our definitions. It is moving through a schedule that began before the sun was born and will continue until the Earth is a cinder. As we approach the final chapter of this story, we must look at the most precise thing uranium has ever given us: time. Because element 92 is not just a source of power or a weapon, it is the ultimate witness. It is the only material in the universe that keeps an honest record of the history of the world. And it is through this record that we finally learned exactly how old we are. As we move deeper into the 21st century, our relationship with uranium is entering a phase of radical reassessment. The trauma of the 20th century, the mushroom clouds over Japan and the abandoned streets of Pripyat, created a deep cultural phobia of element 92. For decades, the quote 31 felt like a failed experiment, a dangerous flirtation with a force we weren't mature enough to handle. But today, a new reality is forcing us to turn back toward the heavy metal. The climate crisis requires carbon-free energy on a scale that wind and solar alone struggle to meet. Suddenly, the destroyer of worlds is being rebranded as the savior of the atmosphere. In Europe, the divide is stark. Germany officially closed its last nuclear reactors in 2023, choosing to walk away from uranium entirely. Meanwhile, France is doubling down, announcing the construction of at least 6 new massive reactors. But the real shift isn't just in building bigger versions of the old machines. It's in the quote, _34, or SMR. These are compact, factory-built units that can be shipped on a truck and installed in remote areas. They are designed to be quote, _35, meaning they can shut themselves down without human intervention if something goes wrong. We are trying to move from the giant, terrifying cathedrals of power to something more like a home appliance, smaller, quieter, and ubiquitous. But as we look toward a future powered by uranium, we must confront the final technical wall, the fuel supply. If we transition the entire world to nuclear power, how long will the uranium last? On land, our reserves are finite, but the ocean holds a secret. Seawater contains dissolved uranium at a concentration of about 3.3 micrograms per liter. It sounds like a tiny amount, but given the volume of the world's oceans, there are approximately 4.5 billion tons of uranium floating in the water. This is nearly 1,000 times more than all the known land-based deposits combined. Japan and the United States are currently developing polymeric adsorbents, essentially plastic ribbons that can be dipped into the ocean to soak up uranium like a sponge. As long as the Earth has oceans, we have uranium.
Others thought it was millions. We were guessing.
Uranium provided the answer. It works because uranium-238 decays into lead-206 with a half-life of 4.47 billion years, almost exactly the age of the solar system. This quote, 39 is the most precise chronometer in the universe. When a zircon crystal forms in molten rock, it accepts uranium atoms into its structure but rejects lead. This means that every single atom of lead found inside an ancient zircon crystal today was once an atom of uranium. By measuring the ratio of uranium to lead, we can calculate exactly when that crystal cooled. It was through this method that we discovered the Jack Hill zircons in Australia, which are 4.4 billion years old. Tiny grains of sand that survived the cooling of the planet's first crust. It was through this method that we finally put a number on the age of the Sun and the Earth, 4.567 billion years. Uranium doesn't just provide us with power, it provides us with the coordinates of our existence. It is the ultimate witness to the biography of our planet. In the end, what is uranium? It is a metal born in the collision of neutron stars, a remnant of a cosmic event so violent it makes our sun look like a candle. It is the fuel that keeps our planet's heart beating and our magnetic shield intact. It is a poison in our basements and a savior in our hospitals. It has been used to erase cities and to light up the dark corners of our world. But uranium remains indifferent to our dramas. It doesn't care about our treaties, our wars, or our climate goals. It is simply moving through a schedule of decay that was set billions of years ago. Whether we use it to build a civilization that reaches the stars, or whether we use it to destroy ourselves, the atoms of uranium will continue to tick. They will be here long after the last human has spoken. They will be in the granite of Finland, in the water of the oceans, and in the bones of our descendants. We are just a temporary structure of atoms that learned how to split a much older, much heavier atom. We have tapped into the primal energy of the universe, and we are now discovering that this energy comes with a price. The responsibility to be as stable as the element itself. Uranium is not just a resource, it is a mirror. It shows us our ingenuity, our greed, and our mortality. It is element 92, the weight of the world, held in a single piece of silver-grey metal. If this deep dive into the nature of element 92 changed how you see the world beneath your feet, please hit the like button and subscribe to the channel. These stories of the elements are the stories of us, and your support allows us to keep exploring the hidden physics that dictates our history. I'd love to hear your thoughts in the comments. Do you think the future of humanity belongs to uranium? Or is the shadow of its past too dark to overcome? Let's start the conversation below. Thank you for watching.